Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're gonna take a look at SpaceX stainless Starship. So let's dive right into it. So what the heck happened here? Now you have to understand, as I mentioned again and again, that Elon Musk hasn't finalized the design yet. So this is another update. This is like fourth update, major update to Starship, and the whole idea is that they're gonna let go of carbon fiber and replace it with stainless steel. As you can see, this was the old system of carbon fiber. So reasons as why they're supposed to do it, it's basically first cost, second structural benefits. So let's dive more into it. Now, if you look at from SpaceX perspective, what's happening actually here is deadline is coming, because in my last video that you can check out here, that I mentioned that the billionaire that gave them the money must have asked some sort of basically what we call posts. Basically, you have completed this WIP, work in progress, kind of some sort of milestones have to be achieved. So I think for that reason alone, because they were missing behind on milestone, they rushed it, and the design is still not final. Now this aspect is very crucial, because if you keep changing the design, at some point you end up in a point where you have spent so much time in design phase alone that you could have lost a significant amount of money for R&D phase alone. Even though your final product may be very good, the lost R&D budget would be so high that your product cost will go too damn high. So as you can see, they rushed the construction of that stainless steel rocket. Basically, this is supposed to be their star hopper. However, it fell over in a wind. Basically, they rushed the construction of this very, very dramatically. And as you can see, this is the very old first interplanetary transport design. Then they changed the design, then they changed the design again and again. So from this point on, if you keep adding up the cost, how long they have spent in terms of development, that starts to pile up. That's why people have a deadline in mind. You can't just keep developing. Yes, you can keep developing and you will always end up with better, but at some point you have to cut, okay, let's go with it, because if you don't, you will keep end up refining, and it's it will never be finished. So that their deadline is approaching, which must be because of that billionaire's contribution. Second, the design is not final, which is very dangerous, because they're supposed to go in 2022, so that's not happening. However, there is one good thing about this. They are bypassing sunk cost fallacy. Now sunk cost fallacy is very, very crucial to understand in business. So it happens sometimes you start to do something and you lose money. Like Samsung entered into interchangeable lens camera landscape, and they were quite good, and they saw there was not enough room to grow into it, and they left it. They cut their losses. So that's one kind of scenario where we call a sunken cost fallacy. You put so much money into it, you did so much R&D into it, you poured your heart and soul into it, but you have to cut your losses at some point. So NASA hasn't done that, because they should have cancelled a space shuttle very early on and progressed with X-33, but they didn't. A loss of life occurred because of that. So sunken cost fallacy is very serious thing. So let's understand this carbon fiber versus steel aspect. Now you have to understand the cost difference between steel, normal steel versus normal carbon fiber. It's very damn high. It's 15 to 30 times to 60 times higher. However, carbon fiber is not that good. Is it better? Yes. Is it that good? I spent 10 times more money, I'm getting even 8 times better performance? No, you're barely getting better performance. Now you will okay, if it's that little, why they are using it? Again, let's say you are talking about Ferrari, why it's made out of carbon fiber. Again, it's $1 million car. It's supposed to have that sort of things. And in terms of rocketry, every kilogram matters. So if you are saying that by changing the material you can save, let's say 100 to 2 tons of material using carbon fiber, they're gonna do it. So that's why we use carbon fiber. It's a bit better, but it's not that much better. In terms of cost wise, it's not that better. However, on top of that, that alone would not be that big of a deterrent. The problem is very hard to manufacture. So far, very few people have successfully come close to building a carbon fiber structure without autoclave. Basically, autoclave is a structure where you put your parts in and you pressurize it, very high pressure with very high temperature, and this sort of thing gives the strength to carbon fiber. So as you can see, this structure is basically cloth. When you build a structure into this, you have to put it into enclave to give it final structural rigidity. However, some people are trying to bypass that stage, but it's not very successful yet. So you can understand it's very hard to manufacture. On top of that, let's say you spend the cost, let's say you did the manufacturing, it is not very resilient matter. This is a space shuttle's carbon fiber composite tile, which was used for thermal protection, and as you can see, this caused loss of life because a foam pad fall into it and it shattered it. Now here's the deal, there was some other structural material that's supposed to be used, that was titanium. If titanium was used here, titanium would have dented, undeniably so, it would have also dented and might have also suffered a puncture, but it would be like a pinhole versus this giant hole. So you can say it's not very resistant, it does not give you a lot of breathing room, like, you know, in terms of error, in terms of damage, it does not give you a lot of breathing room. That's why carbon fiber is, like, you know, being pushed aside. So let's look at the science aspect of it. Now what they want to do is, like, basically they want to do active cooling, same as rocket engines. You can see these small pipes, they always have a liquid fuel or sometimes liquid oxygen running through it to keep the chamber cool, because this chamber can reach upwards of 3000 degrees Celsius, sometimes even higher than that. However, there is no metal that can withstand that temperature. So how do they do it? Basically they have tubes, veins as they call it, and they run cryogenic fluid to it, either liquid hydrogen or liquid oxygen. That way they can keep it cool. So that is one way of doing it. This is called active cooling. And what SpaceX is planning is using same method, but they will have micropores. So basically think of this section is your heat shield. They will have small holes into it, that laser drill holes that would be like a bit bigger than your human hair, but you won't be able to see it. So if you run your hand across it, you won't be able to feel it. If you try to go very close with a magnifying glass, you may be able to see some pattern, but it's very small. The holes are very small. And the idea with that is that they're gonna have cryogenic running into it, and once the cryogenic is heated up because of the re-entry, it will boil off, basically, because it will go from liquid to gaseous, and then it's gonna bleed off through these holes into the atmosphere and take away the heat. Basically it's like sweating. That's all it's happening. It's like you have cryogenic fluid, it's gonna absorb a lot of heat and then it's gonna evaporate away. Now why bleeding liquid CH4? Basically it's colder, it has more carrying capacity than liquid oxygen, and you don't want liquid oxygen near material component. Basically, if you have steel, liquid oxygen can oxidize it, especially in high heat environment. So for that reason it has to be fuel CH4, so it's not gonna oxidize it. However, with all these things, it's basically very simple with so far. However, the back pressure is the biggest concern that I have. Because of this micropores, you have to pressurize the fluid. These are used for anti-icing in aircraft industry. I have provided the link down below. So whenever this plane is never gonna face, like, you know, re-entry condition. Like, this is a thermal image of a space shuttle. As you can see, it's very hot. Whenever space shuttle or things like this re-enter the atmosphere, they are very hot and they are traveling at very high speed, and the pressure there is very high. So if you want to have something that comes out of this hole into this pressure, you're gonna have very strong pumps. Like we do that. This is the reason why rocket engines are so expensive. To feed back into this, we use turbo pumps with a very complicated geometry to make sure you can put because you are going against the grain. This is, let's say, 1000 psi and your exhaust is barely like 300 or 400 psi. Somehow you have to mix those two and not let, like, you know, 1000 psi back feed. That back pressure is the biggest problem in this sort of structure. You have a structure, no problem. Stainless steel is very good at very high temperature, and certain structure can directly handle upwards of 1300 degrees Celsius. So let's say you are doing active cooling. Till this X part, there is no problem with it. But you want to bleed off your energy, dumping energy into the void, basically into the plasma. That's the difficult part. It's not impossible, but the amount of pump pressure you will need to make sure that your liquid methane is first circulated fast enough so it does not, you know, boil off in the wrong place. It boils at the right place, then it, you know, dumps it into the basically super hot, super high pressure plasma. That's very difficult to do. This is the part that, you know, it's bothersome right now. Or they could bypass that. This micropore, they can bypass it also, but they will end up losing a lot more methane. If they bypass this structure, they have to, you know, the budget of methane will go up. So they have to spend more methane for this. So this is the science behind it. Basically, they're gonna use active cooling, same as your rocket engine. They're gonna have micropores that's gonna bleed off the heat, and it will be using liquid CH4. Consequence, they have to somehow figure out how to handle the back pressure. because if you don't, it might blow up. And I'm generally curious what's going to happen when it's going to land in Mars, because let's say while you're doing it, you are flushing the system, but once it's landed, how are you going to keep it clean? Because like the surface area is large. What if dust clogs some of the holes, and what's going to happen then? So it's kind of interesting to see how they're going to solve this sort of problem. So let's look at the history of this. Many people are like, why we haven't used it. Well, we have used it. From Mercury to now, we have used it. Now, first time we have tried something this sort of structure is North American X-15. Basically, the daddy of every space plane is this. Now, this used Inconel X750 alloy. This is classified as super alloy, and it can work at 1300 degrees Celsius, which is barely 200 degrees Celsius less for in terms of re-entry. You only go to up to 1500 degrees Celsius. This puppy can handle 1300 degrees Celsius raw. Basically, you don't have to do anything. At 1300 degrees Celsius, it can maintain its structural integrity. It has been tested, thoroughly verified, and that's the fine part about it. Like, the whole structure gets hot, but inside it you are cool. And of course, you're gonna have some insulation, because while it withstands the heat does go into it. So you have to make sure somehow you have the either cooling system or reflective system. So it's like using a pot to cook your food. The pot is heat resistant, but you don't want to be cooked inside. So these structures are called hot structure, where just heat comes in, your structure can handle it, gets hot, but it's like I can handle this. But you have to somehow make sure that you are not cooked inside. So that was achieved using Inconel X750. Then we come to Lockheed Martin X33. You can check my video here, X33, and they wanted to use metallic thermal protection system. Basically, after space shuttle, everybody realized ceramic systems are very good, but the system that was used in space shuttle, they were very fragile. And in terms of man hours, how much man hour was spent just to check them? That was 60,000 man hours was spent to check each tiles. Tiles are very good, and they worked on a principle of what we call thermal soak. Basically, you heat it up, it absorbs the heat, and it keeps absorbing, and then it slowly starts to dissipate it. It's basically like metal, however, it's doing it very slowly. It's soaking up the heat and then slowly letting it go. That's why you can handle a ceramic block even though it's after directly came out of oven. Don't do with a normal ceramic. It's meant for thermal ceramics. But that's what it works on. It's not that it's taking the heat and directly blocking it. It's absorbing the heat. The internal temperature will go up, and it keeps going up. There is a breaking limit, but generally that is above 2000 degrees Celsius. So once it absorbs all the heat, it slowly starts to radiate away. That's the benefit of it. It's like when the space shuttle lands, you can still touch the underside of it without getting severely burnt. So that's the whole point of it. So instead of ceramic tiles, they wanted to use metallic system. Now, thick metal can directly do this. Right now, and if you want to do this, let's say you want to build space shuttle, but you want to you are okay with compromising, let's say 5 to 10 tons of payload capacity. Right now, titanium heat shield can do this. Like, you just make it thick enough that it can withstand the heat. It is doable. First few Mercury missions did that. It is a doable system. It's just that we want to have maximum payload. That's why we want to find something that is lightweight. And passive cooling system, right now there is another ceramic under construction that is better than carbon ceramic that was used for space shuttle, and it is multiple times better than everything else that we have tested so far. That is Sharp TPS, thermal protection system. Now, the benefit of that can allow hypersonic travel at sea level. It can withstand that kind of heat. So re-entry is like they don't even care about it. So do not think completely new idea that not using ceramic or ablative heat shields. We have the technology, we have been using it. It's just that somebody has to figure out a way to push this material higher than 1500 degrees Celsius. Then you simply will end up with a hot structure. So this was my presentation on SpaceX new stainless Starship. I hope you liked it or learned from it. In that case, please leave a like. If you didn't, don't worry about it. You can dislike it. I will ask you to press dislike twice. And please comment. I reply to all of them. You can also follow me on my community tab. And please subscribe. Press the bell icon if you're free. And as always, thanks for watching.